Welcome to the Explainer. So today, we're looking at something that honestly sounds like pure science fiction, but it's actually deeply grounded in very real physics. We're talking about the space elevator. It's an absolutely massive megastructure, basically a physical bridge to the stars. And it's the kind of thing that could permanently shift us from an earthbound civilization right into an active, interplanetary industrial force. It's a totally fascinating concept, and it completely redefines our relationship with gravity.
Okay, here's our roadmap for today's explainer. First, bypassing the rocket equation. Second, the architecture of the megastructure. Third, crashing the cost of orbit. Fourth, the ultimate geopolitical target. And fifth, our interplanetary springboard.
All right, Section 1, bypassing the rocket equation.
Okay, let's dive right into this. To really understand why a space elevator is such a massive game changer, we first have to look at the fundamental problem with how we currently get to space. Because let's face it, breaking free from Earth's gravity has always been a brutal, incredibly violent process. Our reality since the dawn of the space age has involved exploding millions of pounds of volatile chemical propellants just to shove a tiny metal tube up into the sky. And we're basically just crossing our fingers that the whole thing doesn't blow up, right? But a space elevator promises a completely different reality. Imagine if going to space became as mundane, as safe, and as routine as boarding a cargo train. No massive explosions, no heavy G-forces, just a smooth ride up.
And here is exactly why we need to move past rockets. It's actually wild when you realize this. Up to 90% of a rocket's initial weight is literally just the fuel required to lift, well, the rest of the fuel. You're only left with about 10% for your actual payload and the structure of the ship itself. So we're basically just launching giant gas tanks into the sky. It's what physicists call the tyranny of the rocket equation. And the amazing thing is, the space elevator bypasses it completely.
Moving right along, Section 2, Architecture of the Megastructure.
So, the crucial point here is that we really have to change how we think about buildings. This isn't a tower built up from the ground, like a skyscraper. It's actually a cable dropped down from space. It's this incredibly delicate balancing act relying entirely on Earth's orbital mechanics. You see, at geostationary orbit altitude, which is roughly 36,000 kilometers up, this amazing thing happens. The centrifugal force of the Earth's spin perfectly matches the downward pull of gravity. So if you were to drop a cable from that specific height, the spin of the planet holds that line perfectly taut.
Now, to make that happen, you need 4 critical interconnected components all working in perfect equilibrium. Step 1 is the anchor. This base station has to be positioned exactly on the equator, maybe a massive ocean platform or a fortified land station, just to tie it down to Earth's rotating surface. Step 2 is the cable itself, spanning that massive 36,000 kilometers. Now, obviously, this can't be made of steel. Steel would instantly snap under its own immense weight. We're going to need hyper-advanced materials with unbelievable tensile strength. Think carbon nanotubes or graphene ribbons. Step 3 involves the climber capsules. These are electromagnetic cars gripping the cable, crawling up, using power that's actually beamed from ground-based lasers or solar arrays. And finally, Step 4 is the counterweight. This is placed way out at 100,000 kilometers, which is just a wild distance to even wrap your head around. But the centrifugal force pulling this counterweight outward is what keeps the entire tether perfectly straight and rigid against gravity.
Section 3, crashing the cost of orbit.
Now what's really interesting about this slide is what happens once that delicate balance is achieved and the structure is actually built. The world changes overnight. We are talking about a mind-bending economic collapse in the cost of moving mass into space. The sheer scale of this disruption becomes super obvious when we compare the metrics side by side. Traditional chemical rockets cost anywhere between $1,500 and $5,000 per kilogram, and the transit? It's full of violent high G-force vibration. Now, sure, it only takes 8 to 10 minutes to reach orbit, but your payload is strictly limited by how much fuel you have to carry. The space elevator, on the other hand, trades that speed for pure efficiency. It takes 5 to 7 days to climb, but the ride is this smooth, continuous acceleration. And most importantly, you aren't fuel limited anymore. You have a near continuous stream of cargo cars heading straight to the stars.
And because of that continuous stream, the price plummets to a shocking new reality: $10 to $100 per kilogram. By leaving the heavy power source safely on the ground and just beaming the energy up to the climbers, the space elevator turns a multi-million-dollar launch into absolute pocket change.
And you know, when you turn thousands of dollars into pocket change, space instantly opens up to massive commercial enterprises. We could build clean energy orbital solar arrays at an unimaginable scale,
beaming infinite, clean electricity back down to Earth. We could move heavy, polluting industrial manufacturing entirely off-planet, which would massively protect our biosphere. We could even construct enormous zero-gravity dry docks to build luxury space liners. I mean, imagine telling your friends you've booked a vacation to the asteroid belt. No way, right? But with this, the possibilities are literally endless.
Section 4. The ultimate geopolitical target.
But as with any world-changing technology, there is a very dark side. Because while the economic benefits are staggering, the reality is that whoever controls this monopoly holds the keys to the entire global space economy. The country or consortium operating this elevator would be sitting on the most volatile geopolitical flashpoint on Earth. Because of this, the base anchor would instantly become the most heavily defended structure in human history. We're talking about an installation ringed by multi-layered air defense grids, fleets of warships, and permanent, strictly enforced no-fly zones.
And they have to defend it like this because the stakes are, quite literally, life and death. The source material puts it perfectly. Just listen to this. The tether represents an unfathomable amount of stored kinetic energy. If a terrorist group, a rogue state, or even a sophisticated cyber weapon successfully severed the cable near that base anchor, the disaster would be absolutely apocalyptic. It's known as the whiplash disaster. Just think about the mechanics of this for a second. The entire cable is under immense tension. If it's cut at the base, the top portion, the part holding the counterweight, would violently fly out into deep space. But the bottom portion, thousands of kilometers of super strong carbon ribbon, would fall back down to Earth. And because the Earth is spinning, that falling cable would wrap itself around the equator at hypersonic speed, literally cutting through everything in its path like a giant cosmic scythe. It is a terrifying level of risk.
And finally, Section 5, our interplanetary springboard.
But if humanity can manage that risk, if we can build it and protect it, this megastructure offers something truly awe-inspiring. Because ultimately, the space elevator isn't just about getting to Earth orbit. Let's move on and see how this builds into something much, much grander. Remember that the top of this elevator is spinning along with the Earth at an immense radius. That means it's acting like a giant slingshot. Any spacecraft released from the upper sections of the cable already possesses enough immense velocity to break away from Earth's gravity entirely. We could launch deep space missions without needing a single drop of fuel for that initial getaway.
And this brilliantly illustrates how, because of that slingshot effect, we get entirely new, easily reachable neighborhoods. Mars, Venus, the outer planets, they are no longer distant, impossibly expensive destinations. By building just a single physical string out into the cosmos, humanity would fundamentally transform the infinite, hostile void of space into our next reachable neighborhood.
It's a monumental engineering challenge for sure. It's fraught with apocalyptic risks, but it possesses an economic and scientific upside that is almost impossible to overstate. Which leaves us with one final thought to ponder. Will we take the leap and build our physical bridge to the stars, or will we remain forever trapped at the bottom of Earth's gravity well? Thanks for joining me for this explainer. I hope it gave you something incredible to think about today.